Hi, everybody. Before we dive into the interpretation of the independent sample's t-value that we calculated last time, if you've been following these videos in sequence, I think it's important and actually it's necessary for us to understand something called the degrees of freedom before we're able to exactly interpret what's going on. So I decided to make this a separate video and talk a little bit more explicitly about the degrees of freedom. Okay, so the degrees of freedom, sort of the technical definition, is the minimum number of independent points or units or something that can vary without breaking the constraints of the system. Now, of course, that probably doesn't make a whole lot of sense, especially if this is your first time being introduced to statistics. So I'm going to try to make that a little more digestible. In simpler terms, it's sort of like how many things that can change without changing the data set's characteristics, something like that. And it's going to make more sense as we go through some examples here. So I'm going to try to focus most of this presentation on that. But it's also, if you think of it like what is free to vary in our data set without actually changing the characteristics of the data set itself. Okay, that I think is a more useful definition. And again, this will make more sense once we actually go through some examples here. Now, we typically calculate this by taking the number of times we observed a value for the variable, and then we remove the last one, or it's just all of the times we observed a variable except for that last one, because it's that last one that is unable to vary, as you will see, without changing the characteristics of the data set. So the way that's normally calculated with a single sample is we take the total number of observations, which is represented with italicized capital N, minus 1. Another way to think about this is it's the penultimate observation of the variable's value. Okay. Now let's go through some examples to make this really hopefully make a lot more sense. So let's start with this. For a first example, let's imagine you've got somebody playing blackjack or 21. If you're not familiar with the rules of the game, everybody gets a card that is turned downward and they can't see. Nobody at the table can see except for the player whose card it is. They're able to view that card. And then the goal is to reach a value of 21 total cards without going over 21. And so they can choose to get a new card randomly selected or to stay with what they have. So let's imagine that you've got this player, their card is overturned. Everyone at the table goes, I have no idea what that card could be. It could be any value. It could be any value at all of the available card values, right? So now this particular player then draws 3 more cards in sequence. They get a 3, a 9, and a 5, which totals, of course, 17. Now here's the trick. If the player now says, yes, I have 21, what happened there is they just specified the characteristics of their sample, if you will, or their hand is what we'll call it. They specified that it equals 21, and so now every other player knows the value of the overturned card, or the card that is not overturned, I should say. The one that they can't see has to be a value of 4, because if the system's characteristics have been specified to equal 21, now that card that might have been anything before is sealed. Its fate is sealed, as long as we actually believe the person who said it was 21. So we don't even need to see it now to see that it is a 4, as long as we believe that person, okay? So in other words, we needed to know only 3 of the card's values. There were 4 cards. We needed to know only 4 of those cards' values as long as the system was specified to be a total of 21 in order to then know everything about the system. It specified the system completely. So we didn't actually need to know that 4th card's value in order to know that it equaled 21, because we already knew the value of the other 3 cards and that it equaled 21. Okay, so in other words, that last card could not have varied. This is essentially the idea of degrees of freedom. Now, as I said, normally we calculate this with one sample. We'll take the total number of observations of the variable and subtract 1. That's exactly true here, of course, as well, because we had 4 cards that made up this system, if you will. Would then 4 minus 1 is 3, right? We took the penultimate number of cards, which is the second to last number of cards, which is 3 out of 4. So that's all well and good. Let's try another example, though, that I think may also help to get at this notion of what we're talking about with the degrees of freedom. Let's stick with card playing for fun. Now let's imagine you have a full deck of 52 cards, it's brand new, and then somebody shuffles it up for you, okay? Because I think if you buy a brand new deck of cards, they're sometimes in order. I don't really know. Anyway, so let's imagine you have 52 cards, and they're overturned downwards. So not like this picture here, but they're turned downwards. And you're going to draw a card at random. The first card you draw could be any value of playing card, right? It could be the ace of hearts, it could be the two of diamonds, it could be the king of spades, and so on. It could be any value at all. Then you choose the second card. The second card could be any card value except for the value of that first card. Okay, we already knew its fate was sealed. That first card has already been discovered. The second card now has fewer things that it could be. It could still be 51 values of card, however. And then so on. With the third card, if you already know the value of the first two cards, you've diminished the chances of what that third card could be. It could be only 50 values of cards, right? And so on. And you do that until you get all the way down to the very last card. And now you don't actually need to overturn that last card to know what its value is, because it can't be anything, right? It doesn't have 52 possibilities anymore. It is narrowed down only to one possibility of what that card could be, because the other cards have been observed. And this is an important point, you knew the parameters of the cards. Okay, there had to be only 52 cards. And there was only one of every value of every suit, for example. Okay, and so knowing that, now you know what this card must be. Okay, now in a system where there isn't, there's an infinite number of cards, for example, now we have a real big problem with degrees of freedom, and kind of everything goes out the window. But if you've observed it only 52 times and the parameters are set that it could be only those specified values, now for example, we know it could be 52 cards, and we know there's a certain number of values of every card. Now you've got an issue here with degrees of freedom, where you can specify what that value of that last card is. So again, in this case, we had the total number of observations of the card, which was 52. We had 52 cards in the deck, and we needed to know the value of 51 of those cards to know the value of every one of those cards, as long as I say our rules are set. So that, I hope, is another good example, is that, as you can see, with each observation of the cards, as long as the system is specified, we get fewer and fewer freedoms for our cards to vary, hence degrees of freedom, until we get to that very last one, which is not free to vary at all. Okay, so now let's do one last example that's different, not card players. Maybe this will help as well. So I have 4 children. This is real. I'm not making that up. I have 4 children. And let's just imagine a scenario where I say, hey, I need you all to clean up your rooms. And let's say they each have their own rooms. And I say, and guess what? I'll give you a prize depending on how quickly you finish. If you're the first one to finish, I'm going to give you a big prize. If you're the second one to finish, I'll give you a slightly smaller prize. And if you're the third to finish, I'll give you an even smaller prize. And if you're the last one, I'll get you a very small prize, or maybe no prize, depending on what kind of mood I'm in, right? So if my 10-year-old finishes cleaning his room first, that's great. I now know who's won the contest, right? It's sealed. I can give him his first prize. But I don't know what the order of the next 3 is going to be. So then let's say my 16-year-old finishes her room cleaning, and now I can give her her second prize. Now I don't know the order of the last 2, however. I don't know who's going to finish next. But once I know that my 8-year-old finishes next, I now know the order of all 4. I now know what's going to happen. So in other words, I needed to know only the order of the first 3 to know the order of all 4. Okay. So again, I've specified it's going to be out of these 4 children. There's only so many possibilities of the order in which it could go. And I needed to know the order of only the first 3 to know the order of all 4. So that is another example of degrees of freedom. Now let's talk about this a little bit more and how this applies to statistics. The reason this is all important for statistics is, of course, because statistics, by definition, are characteristics of samples that are trying to represent the characteristic of a population. And so therefore, if we're treating it as if we've got all of the information from our limited sample size, that would be inappropriate. In fact, what we generally do then is that we underestimate the value of the population, or of the parameter is the technical term. We're underestimating the value of that characteristic in the population if we don't use the degrees of freedom, if we just use that n rather than n minus 1. So that's why we mathematically just subtract 1 from the total number of observations. That then prevents us from underestimating the value of the population's parameter. Okay. Now, this is important, however, because that's with only a single sample that we use n minus 1. In fact, for your different kind of statistical tests, it'll be calculated slightly differently because it depends primarily on what are the parameters of this test. So keep an eye out for that, for ANOVA, for chi-squared analyses, and of course for our t-test that we're currently working on. So again, if you've been watching these videos in sequence, the last thing that we did was an independent samples t-test. So for an independent samples t-test, because we have two samples that are independent of each other, it wouldn't make sense to combine them and then subtract 1. In fact, we would need to treat them as independent samples. So what we do is we take 1 away from each of the independent samples. With 2 independent samples, taking 1 away from each, that's of course removing 2 from the entire population, or I'm sorry, the entire sample here. Okay, so in our particular last example that we used, when we calculated a t-value, we had 7 people in one of the groups and 6 people in the other group. 7 plus 6 is of course 13, and 13 minus 2 is 11. So we have 11 degrees of freedom for this little problem that we've been working on. Now, that's important. We're going to need to know that for how to interpret our t-value that we obtained in, I guess it was the most recent video that we talked about. So we will do that then in the next video. Right, a quick recap, of course, is that degrees of freedom are very important to most statistical tests. You'll notice not all, however, because we didn't calculate degrees of freedom for things like correlation. So we don't need to get into the whys and all of that for this particular video. In fact, if you don't understand degrees of freedom exactly, like you're still kind of, it's foreign to you a little bit, it's the kind of thing to continue to think about. That's fine. You could rewatch the video and toy around with it. In the end, though, if you just do it, that's fine. You know, if it says n minus 1, just make sure you subtract that 1, and that's all that is most important for this particular kind of course, this level of course. However, it'll come up in grad school for those of you going on to grad school. Its general purpose, if you just remember this, it keeps us from underestimating the value of a statistic. That's all it really is, or I suppose it's underestimating the value of the parameter. That's all it really does, and the main thing that matters about that. And of course, it's important to remember that the degrees of freedom are calculated differently depending on the actual statistical test you're running. Okay, so just pay attention to that. I'll of course make a point for that for every new statistical test that we run here. Okay, we'll get into the interpretation a little bit more next time. I will see you then. Thank you.